In this video, we're going to define a series and show how series are related to sequences. We'll also carefully define what it means for a series to converge or diverge. We already know that a sequence is simply an ordered list of numbers. For example, we can have a sequence where the first 5 terms are 1, 1/2, 1/4, 1/8, and 1/16, and the sequence will continue on in this pattern. And we should quickly be able to determine that the general term for our sequence will be of the form 1/2 to the n minus 1, and that will be the nth term, a sub n, of our sequence. In calculus, when we consider sequences, our primary interest is in the long-term behavior of the sequence. In other words, we want to know what is happening to the terms as we go further and further out into the series. Do the terms approach a single number, for example, or do they grow arbitrarily without bound, or do they have neither of these behaviors? A concept that is related to sequences but is very, very different is a series. A series is the sum of the terms of a sequence. So instead of listing all of our terms as a list, we're going to be adding them together. So for our sequence that we just discussed, the corresponding series would be the sum 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, and adding all the numbers of the form 1/2 to the n minus 1 together. Like most long sums, we can rewrite this summation and make it more compact by using sigma notation. In this case, since we have an infinite sum, we're going to take the summation starting at n equal 1, going to n equal to infinity, which is just indicating that this summation will go on forever. And we need to indicate the general term that of our summands for our sum, and that is just the general term for our sequence. So here we have the summation, sigma 1 to n equal 1 to infinity, of 1/2 to the n minus 1. While this concept seems easy enough, we're just adding up a bunch of numbers, there's a really important question here that we need to answer before we discuss anything else with series, and that is, what in the heck does this actually mean? If we only had to add up 2 numbers, that would be easy to do even with a calculator. If we had to add up 5 numbers or 10 numbers or even 100 numbers, that's something that can easily be done, although possibly very tedious, using a calculator. However, here what we're actually being asked to do is add up infinitely many numbers. We can start with 1 and add 1/2, and then add 1/4, and then 1/8, and 1/16, and so on. And even after we've added the first 100 such numbers together, there are still infinitely many terms remaining that we need to add. And so what we first need to do when we talk about a series is understand what we actually mean by the sum of an infinite number of terms. As with many things in calculus, such as when we defined a definite integral or the derivative of a function, in order to find an exact value of some quantity, our first step is going to be to approximate that quantity. In the case of a series, our approximations are going to take the form of a partial sum. And a partial sum is exactly what it sounds like. We're going to take part of the entire summation. And so here we're going to define S sub k to be the sum, n equal 1 to k, of the general term of our series. So we're looking at the series 1/2 to the n minus 1. And so given a value of k, S sub k is a finite sum. Even S sub 100, for example, is the sum of 100 numbers, which we can do without any problem. We can find these partial sums, S sub k, for specific values of k by simply adding together the first k terms of our series. So for example, S sub 1 for this particular series is the sum of one term of the series, and our first term we know is 1. And so S sub 1, that partial sum, is simply the number 1. S sub 2 is the sum of the first 2 terms of our series. It's the sum n equal 1 to 2 of 1/2 to the n minus 1. And this would be 1 plus 1/2, which we know is equal to 3/2. S sub 3 is going to be the sum of the first three terms of our series, which would be 1 plus 1/2 plus 1/4. And by converting all of these numbers to fourths and adding them together, we see that this is equal to 7/4. We can compute S sub 4 in a similar way. We're going to add together the first four terms of our series. So this will be 1 plus 1/2 plus 1/4 plus 1/8. And adding those all together gives us a sum of 15/8. And we can compute one more, S sub 5. This is the sum of the first five terms, which would be 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. And this will equal 31/16 when added together. And so here we have the first five partial sums of our particular series. If we wanted to, we could continue this process. We could compute the partial sum S sub 6 by adding the first six terms, S sub 7 by adding the first seven terms. We could compute S sub 10 by adding the first 10 terms, S sub 20 by adding the first 20 terms. We could even compute S sub 100 by adding the first 100 terms of our series together. Notice that what we're doing here is forming a sequence of partial sums. So we have a sequence that we formed related to this series, but the terms of our sequence are not the terms of our series, but rather the partial sums of our series. So this particular sequence starts, we have the first five terms written here on the screen. The first five terms of our sequence are going to be 1, 3/2, 7/4, 15/8, and 31/16. And this sequence would obviously continue on by looking at more and more partial sums for our series. Each of the partial sums in this sequence is an approximation for our series. A partial sum is formed simply by going through the addition process for a series and stopping after a finite number of additions. The more additions we do, the better approximation that we'll have, which means the further we go along in this sequence, the better the approximations we'll get. And so that means it's useful to have a general term for our sequence so that we can then consider the end behavior of that sequence. So in this case, we have the first five partial sums, S1, S2, S3, S4, and S5, and we'd like to find a formula for S sub k, the general term of this sequence. Well, notice here that we have each term is a fraction, and the denominator is simply going to be 2 to the k minus 1. We have powers of 2, 1, 2, 4, 8, and 16, and the power of 2 is 1 less than the index. So for example, if we look at our fourth term, S sub 4, the denominator is 2 cubed, 2 to the third, so 1 less than 4. So our denominator would be 2 to the k minus 1. In the numerator, we have numbers 1, 3, 7, 15, and 31, and we notice that each of those are 1 less than a power of 2. 1 is 2 minus 1, 3 is 4 minus 1, 7 is 8 minus 1, 15 is 16 minus 1, and 31 is 32 minus 1. And so in our numerator, we're going to start with 2 to the k and then subtract 1 from that number. Again, if we look at S sub 4 in this formula, we're going to have 2 to the fourth, which is 16, minus 1, which is 15. And so S sub 4, according to the formula, would be 15 over 8, which is exactly what it is. And you can check with k equal 1, 2, 3, and 5 that the rest of our terms, our initial terms here, line up as well. And so here is a formula for the general term of our sequence of partial sums, and now we can treat this as a sequence and consider the long-term behavior by looking to see if this sequence converges to a limit or if it diverges to infinity. In order to compute the limit of this sequence of partial sums, we can first rewrite the term of our sequence a little bit. Here we have a quotient of a difference over a single term, and so we can write this as the difference of the quotients. So 2 to the k over 2 to the k minus 1 minus 1 over 2 to the k minus 1. So we can break up this across the subtraction in the numerator. And our first term, we have powers of 2 in both the numerator and denominator, and so we can rewrite this using properties of exponents as 2 to the k minus 1. And of course, that simplifies to simply 2 to the first power, or 2 minus 1 over 2 to the k minus 1. And so this is a new formulation for our partial sum s sub k. We have 2 minus 1 over 2 to the k minus 1. Now that we have a nice formula for our partial sums, we can compute very large partial sums for our series. For example, we might want to compute s sub 100. This would be the sum of the first 100 terms of our series. Instead of adding 1 plus 1/2 plus 1/4 plus 1/8 all the way up until we have added 100 numbers, we can simply use this formula shown here to compute this. This will be 2 minus 1 over 2 to the 99th power, since we have 2 to the k minus 1, and here k is going to be 100. And if we were using a calculator, or in this case most likely more a computer, to get an approximation for this number, we would see that this is going to be approximately 1.999 repeating until eventually it stops and we get 842 and then some other things after that. But we actually have 29 nines here in our decimal expansion. So it's 1 followed by 29 nines and then some other numbers after that. So this number is extremely close to 2. And so if we had taken bigger partial sums, maybe we compute s sub 200, s sub 500, what you would notice is that these numbers would get closer and closer to 2. And this would lead us to think that the sum of our series should be defined to be 2. Even though we're adding up infinitely many numbers, the further we go out in the summation, the closer and closer we get to 2. And we'd like to make that kind of behavior exact. And the way that we're going to do that is we're going to define the sum of our series. So this is our series now, n equal 1 to infinity of 1 over 2 to the n minus 1. And again, we're doing a series here going all the way to infinity. We're going to define a series to be the limit of the partial sum. So the limit as k goes to infinity of s sub k. Notice that on the right-hand side here, we're defining the limit of a sequence. This is a very important distinction to make. We're defining the sum of a series by looking at the limit of the partial sums, which is a sequence. And so here, in this particular example, we want to take the limit as k goes to infinity of our formula that we found for s sub k, which is 2 minus 1 over 2 to the k minus 1. And we know that as k gets large, 1 over 2 to the k minus 1 is going to go to 0. And so our sequence of partial sums is going to converge to the number 2. And so here we're going to define the sum of our given series to be exactly 2. So even though it's impossible to physically add up the infinitely many terms in our sum, by looking at partial sums, which are just finite sums, which are easily computed, and then taking the limit as we get further and further out in the partial sum sequence, this gives us an approach to defining the exact value of the sum of a series. We're now going to formalize the ideas in the previous example. We're going to start by letting a sub n be any sequence of numbers. A series is just an expression of the form the sum n equal 1 to infinity of a sub n, so it's the infinite sum a1 plus a2 plus a3, and so on. We're simply adding together formally all of the terms in the given sequence. The kth partial sum of the series is a finite sum that we get by ending the summation after k terms. So we have the sum n equal 1 to k of the sequence a sub n, and this would be a1 plus a2 plus a3 and so on, but ending after we get to a sub k. And so this is a finite sum that we can easily compute by just typing in that a1, the number a1 into a calculator, adding a2 to that, then adding a3 to that, and then stopping after we've added the number a sub k. We're now able to answer the question posed at the beginning of this video about what it means to add together an infinite list of numbers. We're going to say that the series n equal 1 to infinity of a sub n converges to the number s, which we'll write as the summation equaling the number s, or finding the sum of our series, if the sequence of partial sums converges to that same number s. And so the relationship in the middle of the screen is by far the most important defining characteristic of a series, and that is the series n equal 1 to infinity of a sub n is going to equal the number s if and only if the limit as k approaches infinity of s sub k, which is the limit of the sequence of partial sums, is equal to that same number s. And so in order to define the sum of a series, we're going to form partial sums as a sequence of partial sums, take the limit of that sequence. Of course, the sequence of partial sums might diverge, either to positive or negative infinity, or possibly just diverging in general. And if any of those behaviors approaches, then we're simply going to say the series n equal 1 to infinity of a sub n also diverges, in which case there is no sum. Either the sum will get larger and larger without bound, either in the positive or negative direction as we go further out in the sequence of partial sums, or something other kind of weird behavior is happening and we do not get an exact value for our sum. So as we see here, the key to determining the behavior of a series, whether the series converges to a specific number or whether the series diverges, is by looking at the sequence of partial sums and determining whether that sequence converges or diverges. To illustrate how we would use partial sums to determine whether a series converges or diverges, let's consider the series n equal 1 to infinity of 1/3 to the n minus 1 power and determine whether the series converges or diverges. The first thing that we need to do in order to use the definition that we just discussed is to find a sequence of partial sums. We'll first find the first several partial sums and use that to find a general formula for the kth partial sum. We can find the first several terms of our series by starting with n equal 1 and evaluating 1/3 to the n minus first power. When n is equal to 1, we get 1/3 to the 0 power, which is 1. When n is 2, we get 1/3 to the first power, which is 1/3. And continuing on, we get terms 1/9, 1/27, and 1/81. Of course, we could continue on as far as we wanted, but this will at least give us the first 5 terms in our sum. Once we have those, we can compute our partial sums. S sub 1 will just be the first term of our series, the sum of the first term, which is just 1. S sub 2 will be the sum of the first 2 terms, 1 plus 1/3, which will be 4/3. S sub 3 will be the sum of the first 3 terms, 1 plus 1/3 plus 1/9, which will be 13/9. S4 will be the sum of the first 4 terms, 1 plus 1/3 plus 1/9 plus 1/27, which sums to 40/27. And S sub 5 will be the sum of the first 5 terms, 1 plus 1/3 plus 1/9 plus 1/27 plus 1/81, which equals 121/81. We could, of course, continue if we wanted, but this does give us the first 5 terms of our sequence, and this should be enough to come up with a formula for the general term of our sequence of partial sums. The pattern to find a formula for the kth partial sum s sub k here is admittedly a little bit difficult to find. It's not terribly difficult to see that the denominator are powers of 3, and in particular, the denominator of s sub k will be 3 to the k minus 1. Just like, for example, in s sub 4, the denominator is 3 to the third power, which is 4 minus 1. In the numerator, it's a little bit more difficult to find a pattern for these numbers, 1, 4, 13, 40, and 121. However, what I'm hoping you can check is that a formula that works is 1/2 times 3 to the k minus 1. And so if you take the index of each of these partial sums, 1, 2, 3, 4, or 5, if you compute 3 to the k minus 1 and then multiply that by 1/2, you will see that you get the numerator, 1, 4, 13, 40, and 121, respectively. Now, again, this would be a little bit difficult to find in general, but let's take for granted here that we have found this formula for our kth partial sum of this particular series. We can now clean this up like we did in the earlier example. So this will end up being 1/2 times 3 to the k over 3 to the k minus 1, minus 1/2 over 3 to the k minus 1. We have to distribute that 1/2 across the difference in the numerator. And when we simplify this, in our first term, we have our factor of 1/2, and then the rest of the powers of 3 simplify simply to the number 3. And so we have 1/2 times 3, or 3/2. And in our second term, we have 1/2 all over 3 to the k minus 1. Right, so here is a nice formula for our kth partial sum. And so if we want to compute the value of our series, we know that we want to compute the limit as k goes to infinity of our partial sum formula. So here, limit as k goes to infinity of s sub k. This means we want to compute the limit as k goes to infinity of this formula we just found, 3/2 minus 1/2 over 3 to the k minus 1. When we do this, the second term here will go to 0 because we have a constant over a larger and larger number. And so this limit will equal 3/2. And so what this means is, since the sequence of partial sums converges, and it converges specifically to the number 3/2, is that the sum n equal 1 to infinity of 1/3 to the n minus first power, by the definition that we just discussed, will be the limit as k goes to infinity of s sub k, which we just found to be 3/2. So our particular series here converges, and in particular, we know it converges to the number 3/2. So if we add up all of the terms in this sequence, 1 plus 1/3 plus 1/9 plus 1/27 plus 1/81, and as far out as we want to go, we're going to get closer and closer to the value of 3/2. And so we'll actually define the sum of our series to be equal to 3/2.